So we've got, let's say, a surface here, a photoelectric surface. It's a piece of metal that has electrons on it. Of course, it has protons and neutrons as well, but it's the electrons that we're concerned about. We shine some red light on that piece of metal. Let's say one single photon of red light. And let's say that when we shine that one single photon of red light on it, nothing happens. No electrons are ejected. What do we know about that red light if no electrons are ejected? It's not what? It's not a high enough frequency. It means there's a certain threshold frequency associated with this piece of metal, and this red light is not above the threshold frequency. Let's say that we change it up a little bit. We increase the frequency to, let's say, green light. And let's say this time that an electron is ejected from that surface. What do we know about the green light? It's either at or above the threshold frequency. Now, if I have one photon of green light, then I'm going to get how many electrons ejected? One. It's a 1-to-1 ratio, right? If I have 25 photons of green light, how many electrons are getting ejected? 25. If I have 25 photons of red light, how many electrons get ejected? 0. It doesn't matter how many we have. If we're below the threshold frequency, regardless of how many we have, regardless of what the brightness of the light is, no electrons will be ejected. What happens if I increase the frequency to blue light, which is quite a bit higher than green light now? Are electrons going to be ejected? Yeah. Yeah, they are. What do we know about the electron or electrons that are ejected here? What are the properties of that electron versus the properties of the electron that was ejected from the green light? They're more energetic. So this electron is ejected, but it may be barely ejected. This electron is ejected with more energy, more energetic electron than the green one was. What do we know about the number of electrons that are ejected here? If we have one photon, then we have one electron. If we have 25 photons, we have 25 electrons. So the only difference here between the blue and the green is that the electrons that are ejected have more energy. In other words, they're moving faster. It's not that there's more of them. There's more of them if we have more photons, but that's not related to the frequency. The increase in the frequency simply makes the electrons more energetic, faster moving. Make sense? All right. We defined a couple of terms yesterday, the first one being the threshold frequency. And along with that, we said the maximum or the threshold wavelength. Threshold frequency is the minimum frequency of EMR at which electrons begin to be ejected, maybe somewhere in the green range here, okay? Lambda max is the maximum wavelength at which electrons begin to be ejected. Okay? Again, somewhere in the green range here. What we're saying is that, look, red has a low frequency and a high wavelength. Blue or violet has a high frequency and a low wavelength. Green is the threshold frequency or the threshold wavelength there. If we're below green in terms of frequency, then we're red, right? No electrons are ejected. If we're above green in terms of wavelength, higher wavelength, then no electrons are ejected. So you need to be above green for frequency, and you need to be below green for wavelength. In both cases, it gives you blue light, right? Make sense? Blue light is higher frequency, has a chance of ejecting the electrons. Blue light is lower wavelength, has a chance of ejecting the electrons. Threshold frequency, threshold wavelength. Another term that we learned yesterday was work function. You guys remember what that meant, work function? It's related, I'll give you a hint, it's related to threshold frequency and threshold wavelength. There's two ways that we defined this. One was the minimum frequency necessary to eject, minimum energy necessary to eject an electron. And if energy is HF or Hc over lambda, then minimum energy would be H times minimum frequency, or H times C over maximum wavelength. Minimum energy necessary to eject an electron. What was the other way we defined it? It's not just the minimum frequency or minimum energy, I should say, but rather it also corresponds to the energy that's used up in the process of ejecting the electron. So how much energy do you lose due to performing this act of ejecting an electron? The work function. Then we talked about the stopping potential. Once the electron has been ejected, the green one or the blue one has been ejected, maybe we want to stop it, deaden its tracks, stop it from moving. Now, that's not really a photoelectric effect problem per se, because once the electron's been ejected, the photoelectric effect has already occurred. But we may want to stop it so that we can determine what the threshold frequency of the metal is. Maybe we want to design our solar-powered calculator. We want to determine what the threshold frequency of the metal we're using is so that we can determine if visible light will power this calculator. We need to determine the threshold frequency. Get the electron ejected, stop the electron, and then do some work, which we'll see a little bit later on, to determine what that threshold frequency is. Bottom line is, when we stop the electron, we're converting kinetic energy to potential energy. It's a conversion of kinetic to potential, like it is when a car goes up a hill. Conversion of kinetic to potential energy. Car slows down as it goes up a hill. Electron slows down as it goes through this potential difference. Now, that means that 1/2 mv squared, the initial energy, will be equal to the final energy. But we often write this right beside that expression. EK max, the max kinetic energy of the electron when it's ejected, is equal to 1/2 mv squared, but it becomes equal to QV stop after the electron's been stopped. Finally, we had one more equation here that is not on our data sheet in any way, shape, or form. This is a conservation of energy thing. It's one that we can derive, and we have to either remember or derive. The energy that we start with in this whole process, what is it that has the energy? When an electron is ejected by a moving photon, what is it that has the energy to begin with? What is it? The photon, the light, the photon. And the energy of that photon is h times f, or hc over lambda. What is it that comes off of this? Okay, once the photon strikes the metal, what is it that has the energy then? Well, the work function isn't the energy that's the final energy. Yeah, it's the electron, and that's going to be kinetic energy, right? Plus work, because the work function is the energy that's used up. So this is what we start with, this is what we end with, and this is what we use up in the process. What we end with plus what we use up in the process is going to be equal to the energy that we start with. Those are our 4 equations that we can use with the photoelectric effect. Remember, this one is valid in other situations as well beyond the photoelectric effect, but certainly you can use it with the photoelectric effect. And remember, this one is not on our data sheet. So you've either got to remember that or derive that, figure it out each time we go to use it. We had 2 sets of homework last night, 2 sets, I think total of 5 questions, I believe it was. The questions were on pages 716 and 718. I want to go over maybe one question from each of those pages here. Over 2, all right. It's not really a photoelectric effect problem per se, but it's a conversion that we do have to do sometimes. So let's take a look at that. Convert joules to electron volts. We know that 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. We know that X electron volts is 5.3 times 10 to the minus 19 joules. So what we're going to do to find X is take the 5.3 up by multiplying, get it to the top, and then divide it by 1.6 times 10 to the minus 19. That should give us, I think, somewhere in the range of 3.5, 3.4, 3.31. We're going to round that to 2 digits, actually, 3.3 electron volts. Does that make sense? So we can do that calculation in the context of the photoelectric effect for sure, but there's also a lot of other contexts where we might have to convert electron volts to joules or vice versa. Good? Okay, let's take a look at the second page here. And that was on page 718. Let's go over number 2 for this one, okay? Number 2, because you do it one way, you get this answer. You do it another way, you get 0.929. Anybody get 0.932? Anybody get 0.929? If you use joules all through and then convert, you get 0.932. If you use the electron volts all the way through, you get 0.929. Which one's right? Well, they both are. So how can you get two different answers? The constants, 4.14 and 6.63, are rounded values. Like they go further than that, but they give us the rounded values on the data sheet. So every once in a while, something like that happens. We get slightly different answers because we're using not unrounded numbers. We're using rounded numbers. That's why we always want to use unrounded numbers when possible, right? Now, on a diploma exam, um, because you could quite legitimately get two different answers, both of them would be keyed correct. Okay, they would have thought of that. The exams are field tested. The questions are field tested so many times that they've picked up on all that stuff, all the possibilities, and they'll mark both of those correct. So you never need to worry about, oh, I'm doing it this way, but I do it the other way. I get a slightly different answer. Which one's right? They both are. Okay, don't stress over it, John. Okay. All right, blue light number 2 says blue light of wavelength 410 nanometers strikes a metal surface for which the work function is 2.1 electron volts. What's the energy of the emitted electron? What equation do you want to try for this? Keep in mind that all of those equations that we have listed there are perfectly valid. It's just that they all might not necessarily work for us. Try one and see if it works. Which one do you want to try? Okay, good. I counted to 5 with my fingers here, and within 5 seconds, one person gave me an equation there. And he gave me the one that I would try too. Everybody else either just didn't want to answer or weren't sure which equation to try. Listen carefully to what I'm about to say here. If you're not sure which equation to try the last one. If you're not sure which one to use in the photoelectric effect, within about 5 seconds, use the last one. Usually it's pretty obvious which one you're going to use, unless it's the last one. And then sometimes it's not so obvious. So you get a question, it's not obvious, try the last one because it's almost certainly going to be the last one. HF is equal to EK max plus W. By the way, Connor, if you told me the wrong one, it's not going to give me the wrong answer, is it? I might have two unknowns and I have to try something else. That's the worst case scenario there, right? All right, we don't know what F is, but we do know what lambda is. So let's just replace HF with HC over lambda. We're looking for the energy of the electrons, and we're looking for EK, and we have the work function here. I'm going to circle this, by the way, nanometers, so I don't forget to convert that. Do I have to be in joules here, or can I stay with the electron volts here? I can stay. And how come? When can I not stay with the electron volts? When do I need to use joules? When do I need to use joules here? Yep, Matt? If you've got joules in the equation, not even necessarily. A lot of times you can still use electron volts there. Although it might be more convenient to use joules there. You don't have to. Yep. Yeah, when you're using 1/2 mv squared or QV stop. Now, I've got kinetic energy here, but notice I have not subbed in 1/2 mv squared or QV. I can use the electron volts here. As soon as I sub in this or this, I got to use joules. Okay, I have to. I'm going to use the electron volts here. 4.14 times 10 to the minus 15 times 3 times 10 to the 8 divided by 410 times 10 to the minus 9 equals EK plus 2.10. Now, anybody tell me why I used electron volts? I know that I can, but I can also use joules. Why did I go with electron volts here? Yeah, I already got electron volts in the question, right? If I go to joules, I have to do a little bit more conversion. And the answer's in electron volts as well. Now, if you're confused about when you can use joules and when you can use electron volts, what should you do? Sorry? Just use joules. Always use joules. Because joules always works. Electron volts usually works. Joules always works. If you get confused about when you can use the electron volts and when you can't, just don't do it. It's sometimes less work to use the electron volts, but it's never wrong to convert to joules. All right, let's calculate this now, see what we get. Let's say 4.14 times 10 to the negative 15 times 3 times 10 to the 8 divided by 410 times 10 to the minus 9. And then we're going to subtract from that 2.1 electron volts. Gives me an answer of 0.929. Okay, good. Done. If you use joules through this question, 6.63, and you converted this to joules, then you're going to end up, I believe, with 0.932. Okay, both would be marked correct. I don't know which one's better, to be honest, okay, because I don't know which one's rounded more, the 6.63 value or the 4.14 value. Good? Connor, is that good? All right, I want to do one more example, and then after we're done that example, there's a couple practice problems that I'm going to assign for you, and then we will take a look at the whole experimental setup that we talked about for determining what the threshold frequency is and other stuff as well, for that matter. Using table 14.1, determine the maximum speed of electrons emitted from an aluminum surface if the surface is illuminated with 125 nanometer UV light. This is wavelength, and it's measured in nanometers. We want to convert that to meters. We want to find max speed. On table 14.1, you're going to find the work functions of various materials. And I believe the work function for aluminum, somebody double check this, I believe it ends up being 4.08 electron volts. All right, which equation do you think you want to try here to find the max speed? You know, let's write down some givens here, actually. We're looking for max speed. We've got the work function. We've got the wavelength. Looks like that's all we got. Which one do you want to try?
The last one.
Okay, so Connor went to the last one right away. Didn't even let me count to 1. That's okay. Look at all of them. Don't get too tunnel vision on the last one. Look at all of them and see if you can figure it out. But if you can't, in a relatively short time, then go with the last one. Let's try that. Let's try the last one. The one you said first. Connor, you were right the first time. Now, we don't know what F is, but we know what lambda is. So let's replace that. HC over lambda. We don't know what EK is. We don't even want to find EK. We want to find V. So let's replace EK with 1/2 mV max squared. And then W we have. Joules or electron volts? Joules or electron volts? We have to use joules here, right? John, why do we got to use joules here? Why do we have to use joules? Because of the way that it is. Truer words have never been spoken here. Sadie? Yeah, as soon as they introduce 1/2 mv squared, I've got to use joules. If that confuses you, then always use joules, even though sometimes it's a little bit more work. So let's go with the joules value for Planck's constant. Lambda is 125 times 10 to the minus 9. Mass is the mass of the electron because it's what's ejected, right? And the work function, work functions in electron volts, what do we got to do? We got to convert that. 1 eV is 1.6 times 10 to the minus 19 joules equals 4.08 eV equals X joules. X ends up being equal to what? This goes up. This goes up. It's going to be somewhere around 6 point something times 10 to the negative 19. Thank you, Sadie. 6.528 times 10 to the minus 19. So let's plug that in here. All right, let's calculate this now. 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by 125 times 10 to the minus 9. Now be careful of the order you do this in. Let's subtract the 6.52 because it's not attached to the V. Now let's times that by 2. Let's divide it by 9.11. And then let's square root that. 1.44 times 10 to the 6 meters per second. If I illuminated that with a higher frequency, how would that affect the number of photons that were ejected? Higher frequency, how would it affect the number of photons? It wouldn't. If I had a higher frequency or lower wavelength, how would that affect the speed? They would be moving faster because they're more energetic, right? Higher frequency photon, faster moving electrons, more energetic electrons. I'm going to give you a couple questions to go with this for homework on page 719. They are homework, not working on class right now because I want to cover that one last thing before class is over. Take a peek at the diagram on the board here. In the diagram on the board, you have an evacuated tube. Evacuated means that all the air has been sucked out of it. There's no air inside it to get in the way of anything. At either end of this tube, you have a metal surface. One surface is a collector, one is an electron emitting metal surface, called a photocathode. When when photons of sufficient frequency strike that metal surface, then the electrons will be ejected, if they're of high enough frequency. Now, notice we also have this hooked up to a power supply. Power supply which generates an electric current and sends it through the wire. We also have it hooked up to an ammeter, which measures electric current. When we turn on our power supply, we get electrons flowing this way, which causes the collector to become positively charged and this electron emitting metal surface to become negatively charged. We shine these photons on this electron emitting metal surface. If these photons are above the threshold frequency, then the electrons will be ejected. Now, you can see quite clearly here that we have 3 photons striking it. We have 3 electrons that are ejected. So these photons must be above the threshold frequency. They're causing electrons to be ejected. Now, these electrons are attracted to this positive collector. They're going to be attracted over this way. So they're going to speed up over to this metal collector. And then we get an electric current that's going around this way. Right? We had this big gap between the collector and the metal surface. But now that we have electrons flowing from the metal surface to the collector, we have an electric current going all the way around here. So the reading on the ammeter is something. Okay, there's a reading on the ammeter because there's an electric current. Got it? This doesn't show us anything right now. We have the photoelectric effect taking place, but it doesn't do anything for us right now. What I want to do to make it do something for us is reverse the polarity of the power supply, such that this collector is no longer positively charged. We want to make it so this collector is negatively charged, and so that this metal surface is positively charged. Now, when these electrons are ejected, they get repelled by the collector. So they start going over towards the collector, but they get repelled and they slow down and eventually stop. If I shine a certain frequency of photon on that metal surface, and I measure the stopping potential, the potential difference required to stop these electrons, then I increase the frequency to a higher value and see what stopping potential stops the electrons. And then I increase it even more and see what potential difference stops the electrons. Then I have a nice little data table. Frequency and stopping potential. Hey, one quick question here before we move on. How do I know when the electrons are stopped? Good. There's no reading on the ammeter. The current would stop. Good. So we can measure the frequency of these photons. As long as they're above the threshold frequency, they'll cause the electrons to be ejected, and then we can determine what the stopping potential is for each of those different frequencies. We might get a table that would look like this. Now, we could actually plot a graph of that table. We don't usually do that, but we could. Usually what we do is convert that table into an analysis table. Instead of being F and V stop, it would be F and EK max. We would find the value of EK max by simply multiplying each stopping potential by the charge. And then we plot that graph, EK max versus frequency. So let's say that we do this analysis, or we do this experiment, and we get a table that looks like this. Frequency in hertz and EK max in electron volts. Connor, question? No, we can't do this. I would love to do this one actually, but we can't. What are we going to plot here? Well, we plot EK on the y-axis, we plot frequency on the x-axis. This is the big takeaway from what we're doing here today, okay? What you see on this page. The graph that you're going to see here when we plot this is going to look something like this. It will every single time be a straight line, and it will every single time be a straight line that does not go through the origin. It's not like the 1 over di versus 1 over do that you plotted in your last lab. It's not sloping downwards, it's sloping upwards, but it doesn't go through the origin. Now, how do we deal with a graph, any straight line graph? Y equals mx plus b, good. So let's write that down. For this graph, we say y equals mx plus b. And then what do? We start replacing things, right? What do we replace y with? What does y become? EK, kinetic energy. And m becomes slope. What does x become? F, the frequency. Is there a y-intercept here? There is. You don't see it going through the y-intercept now. No, it doesn't cross the origin. Because it doesn't cross the origin, there would be a y-intercept. Now, it's below the x-axis. We might not be able to determine what the y-intercept is. Maybe, maybe not, but there is a y-intercept. It's negative something, right? So we can't get rid of that. What's next? Now that you got the equation for the graph, what's next? Oh, you guys know this. Come on. What is it? We can find the slope, but even before we find the value of the slope, I want to find out what the slope represents. Yep. Yeah, you got to find a formula that matches it. Which equation that you know, maybe it appears on your data sheet, maybe you have to derive it, has both EK and frequency in it. The last one, yeah. HF. HF is equal to EK max plus the work function. Now let's rearrange that to take the same form. And when we do, it's going to look like this. EK is equal to HF plus the work function. Agree? Is that okay? Yeah. Let's start crossing off things that appear in both. EK appears in both. F appears in both. What are we left with? Slope is equal to what? Sorry, I should have crossed off this F. Slope is equal to what? H. The slope was attached to F. H is attached to F. The slope is equal to Planck's constant. You want to find Planck's constant. How do you think Planck's constant was determined in the first place? Plot an EK versus frequency graph. The slope of the graph is Planck's constant. It will be, for this graph, the value would be 4.14 times 10 to the negative 15 or somewhere close to that, because we're dealing with electron volts, but it would be 6.63 if my y-axis was in joules. Okay, what's next? Y-intercept. Y-intercept is equal to what? Sure, this shouldn't be plus W, should it? This should be negative W. So that means that the y-intercept W is equal to negative W. B is equal to negative W. So if you take the y-intercept here, let's say it's negative 3. What's the work function? 3. Negative of the y-intercept, which will be a negative value. Negative of a negative value gives you a positive value. Sometimes it's nice and convenient just to read the y-intercept off and give you the value of the work function. Sometimes it's not. Sometimes you've got to do this to find the work function. Instead of taking the y-intercept, you've got to say h times the threshold frequency. Now h is what? Where does h come from? Don't ever use the value that's on your data sheet if you're using it in the context of a graph. Get it from the graph. What's h come from on this graph? The slope. So if you need to find work function this way, get the slope of the graph. What's the threshold frequency on this graph? Anyone take a stab at that? The frequency at which electrons begin to be ejected. Yeah, it would be the x-intercept right here. Look at this, guys. If the frequency is below this value, then electrons aren't ejected. If the frequency is above this value, look, electrons are ejected with a certain kinetic energy. So you can find the slope giving you Planck's constant. You can take the y-intercept and give you the work function. You can take the x-intercept and give you Planck's constant, the threshold frequency. But you can also find the work function. If you can't get it from the y-intercept, then you can get it from h times f0. Just make sure you use data here from your graph, not from your data sheet. Yep. Yeah, that's a good question. Well, we define that as the threshold frequency. Yeah, so you know what? We'll say it would be exactly, I think, because the point at which electrons began to be ejected with no energy, so they've been ejected, but they're not doing anything. No, it would have to absorb energy to get it ejected. They just wouldn't go anywhere unless they had kinetic energy. Make sense? Realistically, you're above the threshold frequency and it's going to have kinetic energy, right? But that theoretical threshold value is that point where they would have no kinetic energy. Good? Yep. Say that again, sorry. So if you use this equation, not necessarily in the context of a graph even, I don't think, but HF is equal to EK max plus W. If you did it with a frequency that wouldn't work, then you'd end up with a negative value of kinetic energy, which wouldn't have any real world significance, right? Other than to say, oh, you need this much more. If you got -3 for the kinetic energy, that means the electrons would not be ejected. You'd need 3 more in order to get electrons ejected. Okay, so if you get a negative value for EK, you know you're below the threshold frequency. Good? Here's another graph, all kinds of graphs that we could see. Here's another one. Largely, you got to use your graphing skills to determine information from graphs, right? The only reason I went through that last graph is because it appears on tests and exams often. So I thought we might as well go through that one specifically. We could easily see another graph like this one, EK versus intensity. What would that graph look like? Tell me what the shape of that graph would be. How about this? Anybody tell me why the graph would look like this? Yep, Spencer? Yeah, the intensity is the number of photons. So I got 1 photon. Is an electron ejected? Well, it looks like in this case it is. If I have 2 photons, how does that affect the kinetic energy? It doesn't. If I have 1,000 photons, how does that affect the kinetic energy? It doesn't. So kinetic energy versus intensity, they're not related to each other, right? We have a kinetic energy here because we're above the threshold frequency, but as a function of intensity or number of photons, it's irrelevant. Okay. So be aware of things like that, right? This is the most common graph that we see with the photoelectric effect, but we could also see other things like this. Just be aware of them and be ready for them. All right?